Okay, good afternoon, everyone. Welcome to the first MITP NITheCS Seminar. So I think Amanda doesn't really need an introduction. Know her. She's visiting us from UCT, very kindly agreed to give a seminar. So Amanda is going to talk about what we can learn from a growing sample of fast radio bursts. It's not actually my field, but I think I'm not getting them correctly. A cosmology wishlist. So, Amanda, please take it.
Thank you guys for hosting me. I actually grew up in Germany, but I swear I remember none of it. It's interesting. So I've got my various groups logos listed at the bottom, and I am always grateful to the NRF who funds me very graciously. And you can see we try to bring together. There's a Feynman diagram for those of you in MITP and a radio telescope. We try to bring together cosmology as so it's really quite important, some of the work we do. And I'm now also affiliated with AIMS, which, if you don't know, is the African Institute for Mathematical Sciences in Muizenberg in Cape Town. So I'm going to talk about various work today, and some of my collaborators' names are up here. In orange are all former students or postdocs whose work I'm also talking about, so that you see them. And when you see them in the wild, you know who they are. So our group photos always tend to be at AIMS. We go every second week. And I just thought I would introduce you briefly to some of the group members. So Jakombe is a postdoc, Kira and Venu over here are students, PhD students at UCT. Shajid and Marissa are two other faculty members. Shruti is my PhD student who's about to graduate. Thesis was just finally approved. Tato is in the back over there, Shajid student, and Surajit is a postdoc who's just moved to Poland. And new group members who have not made it onto the photo include Zanos in the audience. She wouldn't even take a photo quickly to add, but we're very excited to have her. I'm sorry for your loss. And a bunch of other students and postdocs you can see listed on the right. And yeah, there are always opportunities to visit. So I actually just emailed and said, I'm going to be passing through, can I give a talk? If you guys ever are coming through Cape Town, don't be shy, just send an email and say, I'm giving a talk. I'm passing through, can I give a talk? We'd love to have you. There are opportunities to spend weeks at AIMS if you want, all expenses paid, if you teach. And if you just want to do a research visit, that's also possible. And I put recruitment because we are always, you know, the life cycle. We're always hiring students and postdocs. So just bear in mind what we work on, and maybe you'll find something that's interesting to you. So in terms of a kind of brief outline of like, where is the field? What is the outlook? How am I getting into where I'm going? Cosmology, do any of you actually work in cosmology? Sort of, okay. Don't look happy about it, but I think that's fair. It's a field that, you know, was like barreling towards concordance, and we thought everything's working. This is great. Every bit of data is bringing us closer and closer to the same results. And then we hit this massive crisis, I think triggered by the Hubble constant, which I'm going to talk about briefly. But there are other little crises that are sort of appearing, where cosmology as a field is getting greater accuracy, but worse precision, right? So it's all good and well that the error bars are getting smaller. When they don't include each other, you're in trouble. So there are many ways forward, one of which is to look at astrophysical sources as possible new measures for cosmology, and I'll talk about fast radio bursts to that end. And then I'm going to tell you about the higher-axis experiment. And if nothing else, you should leave with this idea that there is an amazing interplay to be had between experiment, radio cosmology, astrophysics, high energy physics. They're all linked together, right? They're all the problems that we try to work on are completely connected, even if they don't seem to be. And I've got the Nobayama 45-meter radio telescope only as background for this image, because there are radio telescopes, I think, on pretty much every continent. And that's a particularly cool one. So in terms of why do I say cosmology is in crisis, the very big problems that have been kind of loitering for decades is the not understanding what dark matter is, not understanding what dark energy is. These are really large. Inflation is like a nice theory that predicted some of the observations and fits with the observations, but has no real origins from a fundamental theory. So it's a heuristic. You know, you can draw a drawing and I can give you a scalar field, but it's not, doesn't derive from a real theory, and that's really bad. It turns out I didn't know this a few years ago, but there's a missing baryon problem. So we think that 5% of the universe is essentially baryons. A third of them were actually missing. And so there's these little astrophysics puzzles everywhere. My best is discovering that galaxy formation is not fully understood. I would have thought it's a trivial angular momentum conservation, but the simulations don't really match. And then to me, the biggest slap in the face for cosmology is this Hubble tension. And I'm old enough that when I was a student, the professors just said to us, it's 50 or 100, but probably somewhere in the middle, we'll say it's about 70. And all the error bars were plus or minus 50. So they fit in completely very well. You can see here, right? And as time, so this is like roughly when I was a student, and as time has gone by, the error bars are getting smaller, but they're excluding each other. So that is a profound problem, unless you think somebody's made an experimental error. And I'll just show you how bad it is, right? We're in the process of putting out a new version of this table where FRBs are on it now. But you can see that the data falls into early and late categories, and the error bars don't all overlap, and the central results are quite far off, and they're not getting any closer. So it's a real problem when you have this many measurements and they're not really talking to each other. So either you say, well, something's completely wrong with one experiment, but it's very unlikely that everybody who's doing CMB type early universe experiments is getting it wrong, or everybody who's building distance ladders is getting it wrong. It's possibly telling us there's something about the universe that we really don't understand. There's some evolution that's happening that we need to understand. And that's quite a big, profound problem. So there are different ways to solve problems. This is my kind of approach to things. Got rid of all the fancy transitions. It's better to speak to you instead of you focusing on the thing, and then we have time at the end for people questions. So the first step is always say, have they gone wrong, right? So we look at all the existing data, methods, analysis. I don't do any of that. I assume these people know what they're doing. Other people do that. The second step is to consider new physics. So I do lots of that because that's the fun stuff. To think, well, actually, is dark energy maybe evolving? Is there a dark matter component that is driving, that behaves differently with gravity and is driving this change in the acceleration of the universe? Is there some new physics that we don't understand? And if there is, then we need to develop a new theory. And then we can't just test it against all our current observations. That's what most people do. And there's no way to know the difference between that theory and what we currently have. So you have to make new predictions. And new predictions have to be able to rule out a theory. You cannot rule out a theory with new predictions, with new observations. They don't have to be observations like tomorrow, but observations at some time frame, then your theory is toast. So this is really like the way of thinking. And then you probe your theory in every possible way. Okay, so we're going to talk about astrophysics today, but this is really, and then you go back and you say, well, how does this fit with existing data? So this is my approach to everything. I think most of you know more than me about radio astronomy, so I apologize for the slide. But there is this immense potential for radio cosmology to solve many of these problems, because it's a data-rich field for which we are building swaths of telescopes. So many of them are coming out. It's already proven itself as highly compelling because of all this like host of great observations. And you can see the different wavelengths of telescopes and whether they have to deal with dust or not. And radio is sitting in this lovely place where the wavelength is such that we don't have the same problems that some optical telescopes have on Earth, and so they have to go out into space. So there's immense potential for discovery. All of these things were first discovered in radio, believe it or not. And the question is, what's next? So the next is fast radio bursts, which were discovered by Matthew Bales, Duncan Lorimer, and Mara McLaughlin. And then they won the Shaw Prize, I think, 2023, and the discovery was 2007, the first one. They were convinced that the first one was not real. And when Matthew tells the story really nicely, but he had made some mistake as a pulsar astronomer announcing a major thing that turned out not to exist. And so he was very scared to talk about the FRBs. And then the second FRB that they discovered they always saw a pulse at lunchtime. And so it's just not possible. Like, how could an astronomical object know it's lunchtime? So of course they checked the microwave, and if you put something on for 30 seconds and then you open the door without stopping the microwave, there's a little burst of radiation. Now you'll stop the microwave first, right? Do you know what I'm talking about? When you open the door without actually pressing stop, there's a little burst, and the telescopes were seeing that little burst of people prematurely opening the microwave. And so they realized, okay, this is not a real signal. So they had to even think even harder about what they had seen, if it was real or not. But they are real. And my entry into the field, I'll tell you a little bit about some of the papers that I've written. My entry into the field was from chatting with radio astronomers who work on magnetic fields in the universe. And they said to me, you know, there are these weird objects. There are only like 20 of them observed. And there are lots of theories, and we don't really know what they are. Like, maybe we can talk about this. And so I set my students the task of, let's understand all the theories. Can you imagine there were more theories, 47 theories, for like 20 odd observations? So when we put out this wiki, which is probably badly in need of work, but when we first put out this wiki with like, this is each theory and this is how you rule it out, there were more theories than data. Now there are thousands of observations, only a few years old. So the field has completely exploded with data, and it's still coming huge numbers. So the first paper that was the theory paper, but the first paper that we wrote trying to use fast radio bursts as cosmology yardsticks over here was 2017. And we did a simulation for, I'm going to show you a little bit now, but we did a simulation with about 1,000 FRBs, and I had this whole argument with Gainsler saying that's really not a lot. And he was like, it's a huge number. We're never going to get 1,000. I was like, you get 1,000 in a night. I don't understand. I thought there's supposed to be so many. And it was like this mismatch in culture. But of course, now there are tens of thousands potentially to be observed. And so there's really a lot to be done if you can see the potential in the field. So just to tell you a little bit about what we think we know, they are roughly millisecond duration, so they're short-lived, hence the fast. They're in the radio, which is a very wide frequency band, as you know. Some of them are localized to hosts. By hosts, I mean host galaxies. Some of them are not. Means you see them in the sky and you can't work out which is the nearest host. And the localization methods are relatively simplistic. It's an overlay, right, of where you have an optical signal as well, and where you can see them that they've been localized. A tiny fraction of the parameter space has been observed, because we only see little patches of the sky at a time, and they're all still being, the telescopes are all being built still. Possibly the weirdest part is some of them repeat, not all of them. And one of them seems to have a kind of periodic repetition, which is really weird. Yeah, question.
Is it expected that the ones that you can't localize, because there maybe is no optical signals, is it expected that there's maybe some different physical mechanism that produces them?
It could be, but they're all expected to have hosts because they should be in mass-forming regions. So they should be like where stars are. They're not in like empty space. So they should have hosts, but it's the limitation on the observation. And the difficulty with fast radio bursts is everything is an observation bias. So you can only see something that's bright enough to see. So you see the repeaters because they're bright enough to see repeatedly, but the ones that you only see once, is it that the rest of them weren't bright enough, or is it that they've only gone off once? Or did we just miss it because the telescope wasn't always looking? So it's like this whole host of problems that if you can metaphor that into your whole life, but like understanding what we're seeing is still not there because there's like everything is quite patchy. The exciting part is they're at cosmological redshifts. You know, someone said the other day, why can't we do all of this with pulsars? And we just can't see them far out enough. So the fact that you can see them at cosmological distances mean they can be cosmological, like candlesticks or yardsticks, whatever you want to call them. They're brilliant traces of their source environment, so we can learn about the universe around them and between them and us. And the polarization, this may not seem important, but it's not all one type. So for those of you who are interested in very stringy things, there was a theory by Vachaspati that they would be cosmic strings, right? Why not? There are stringy people here. Yeah. So you imagine a cosmic string overloops onto itself and cuts off. That emits radiation, and it emits in the radio. So if you had like cusps forming, you would be emitting radio waves. And there's a calculation that Vachaspati did, and we also did a follow-up paper, but you only get one form of polarization, and so we gave up once they were observed with the other form. Then more observations came about, and you get both. Okay, so it's actually possible that explains some of them. There's a host of possible theories. Cosmic strings is just one of them. Separating out what is cosmological from host is really important. And I'm going to explain that as well. And there's a whole lot of outliers going on, plus a host of theories. So I'll explain to you in a little bit why magnetars seem compelling, but they can't explain all the observations. So it's almost guaranteed that they're going to be catalogs, classes of these things. We're just not there yet. Yeah, no, that's for sure.
Has there ever been one observed in localized galaxy?
I'm coming. You have to wait. I'm getting it. Okay. So the dispersion measure, you saw I mentioned DM. This is kind of the most important part. So as they travel from their host to us, they are traveling through the intergalactic medium. And the signal is being dispersed. So different frequency components are being slowed down preferentially. So they arrive in this 1 over nu squared, 1 over frequency squared sweep that you see over there, okay? And so you are measuring essentially the number of electrons between the object and us. And if you think about cosmology, cosmology is living inside that number of electrons, and hence all the potential to do cosmological stuff. The dispersion measure being large means they're very dispersed, tells us that they're far enough away that they're cosmological in origin. And most of them should have a host galaxy, though we don't know all the hosts, and they're not all the same type of host, which is a little strange. So in terms of cosmology, as I said, that little NE is everything to do with cosmology. And when I first started looking at this, I was busy obsessing about curvature. So in cosmology, there's this whole idea that the universe is exactly flat, but it's extremely unlikely. And the data agrees with flatness, but has a slight preference for a closed universe. And that's just never really gone away. And partially it's because there's a degeneracy between curvature and acceleration, so dark energy. So if you look at the Planck data, you only get results for one relative to the other. You have to set one of them to 0 to get the results. So to really constrain the two, you need to do more stuff, which we will do with 21 centimeter observations with Hyrax. But curvature is not really dead, okay? So the question is, if you had lots of these fast radio bursts, could you get a constraint on curvature? That was our first, let's just play with fast radio bursts. And we have all these astronomy terms that are sitting in here that you use, the baryon mass fractions, etc. And the key one is this guy here. FIGM is the fraction of baryons in intergalactic medium. There's a number we looked up from astronomy papers, okay? And so we want to extract this cosmological information. We know very well how to subtract off everything to do with our Milky Way, and also the halo, which is not drawn on here, from pulsars, the galactic pulsars. And then the total, the relatively large unknown is the dispersion measure that belongs to the host. Okay, so if I get lots of bursts very far away, the relative contribution of the host should be small. But if the bursts are not far enough away from us, the relative contribution can be large and make it hard to do good cosmology. And so our first sort of stab at this, on the one hand, was very good because the results are completely orthogonal to CMB type results. And so we get the ellipses are in different directions. And so you would think you'd be able to get good constraints. But the reality is what you're really constraining is omega baryon, not really omega curvature, because you're probing the baryons, right? And what Tony Walters was my PhD student at the time, and now he's a postdoc with Hyrax. What he figured out is that the FIGM that we were using, we just took as a parameter given to us by the gods of astronomy from their papers, but actually it was the largest unknown in our work. And the cosmology constraints are much stronger. So if we take the cosmology constraints as our priors and allow the values to vary and get FIGM as a free parameter, then if you were to measure FIGM of 0.8, that solves this missing baryon problem. So that's a problem I mentioned earlier, where a third of the baryons are assumed to be somewhere in the warm, hot intergalactic medium, but they're not observed in any way. And so we basically said, if you can measure this value, then you can find these missing baryons. This was in 2019. And in 2020, when all of us were dealing with COVID, they made these measurements. So here's my little burst coming out of its host galaxy. This is the visualization of that dispersion measure I was explaining to you. If your photon is traveling through vacuum, then all the different components will travel at the same speed. But if it's traveling through some kind of medium, then they get slowed down preferentially by frequency. And you see that the different components will arrive at different times. That's that sweep. And so you are probing this missing matter, these baryons. And with only 4 localizations, they completely solved that problem. The missing baryon problem is effectively done with 4 FRB observations. And there was a very nice Nature paper in 2020 with that. So that I thought was kind of amazing. The 4 bursts were very well localized. You can see the redshifts are, to me, that's low redshift. That's why I asked today what you guys consider to be high redshift. It's relatively low redshift. What I found very cool is they're all near the edge of their host galaxies. So like, is there some physics mechanism that drives them to the edges? Or is it that we can only observe the ones that are at the edges because the light can't make it through? Certainly it means we don't have to worry about the host DM, right? Because it's coming from the edge. So our FRBs spread like butter on toast, or they're just on the crust kind of thing. So it makes it very interesting to try to understand what you can learn from these observations. And there seems to be this idea that they most likely come from some kind of neutron star or magnetar type event. And I'm going to come back to that in a minute. I just want to walk you through a host of cosmology potential. So firstly, dark matter, right? So we know dark matter causes lensing, and you get all different types of lensing actually from dark matter. There's, if you have machos, very large dark matter objects, then you would get like double copies. You can also have micro lensing from little ones. But the point is, if you had, say, some kind of macho, so a very massive compact object that is like a primordial black hole or something, then you would get an exact copy of your FRB, but at some delayed time. And so looking for those gives you a way to constrain the fraction of dark matter that can be made up of primordial black holes. And you get these constraints, and they're very, very good because the data is very good and preserves information that you would otherwise lose. And then you can, looking at the substrate, just to be clear, sorry, you're not seeing them. So it's from the absence of an observation, right? It's an absence of that repeated observation. You can also get information about the substructure and get better constraints. You can look for lensing. If there's no lensing, as these guys saw from 110 of them, then you get novel constraints for the fraction of primordial black holes that could be making up dark matter. So we did something very simple here. This was like a really simple project, which is we said, what happens if you had just any modified gravity theory codified by science? Just put in a modified gravity theory. So I don't just have a regular Shortshot metric. Do those constraints still hold? And the answer is no. It can really weaken those constraints because the different theory of gravity acts like a kind of scattering screen, and so you would not be able to see the copies. And so you have to really be extremely careful about what you're constraining, right? So you're only constraining the fraction of primordial black holes and then like the simplest Einstein gravity theories. Then, of course, you can do a lot for dark energy, but it's very hard if you can't get past redshift of 1. If you get lots of bursts at high redshift, then great, but imagine how hard it will be to get them at redshift 3. I don't know if we will. People say that we will, but I don't know if that's the case. But if they are at that high redshift, you can ignore the host completely because the relative contribution is tiny. If you can associate them with gamma ray bursts, then you can constrain the equation of state of dark energy. So you have the 2 observations to help you. It gives you redshift information. With 10,000 of them, you can get phenomenal constraints on H0. And I've put this last line because it's very exciting. But if you put together FRB and gravitational wave observations together, you get low redshift verifications of what you're seeing in the early universe. And the first observation of an FRB coincident with the gravitational wave, there's no claim that the 2 come from the same physics yet, was reported in the Astronomer's Telegram. It's not yet published, but they just released these things to tell you they exist. So Chime basically saw an FRB. Date is over there. It's 6th of February 2025, and A means it was the first one seen that day, and it was 1 minute after this merger, the binary merger that's either a black hole neutron star or neutron star neutron star. So it's possibly, they worked out the likelihood of them being unrelated is 0.01%, but of course likelihoods don't really mean anything unless you really understand them. So if you get coincident events, there's going to be a lot to be done, right? I wish I had that data because this paper will be extremely interesting. there's also lots of weird physics you can constrain. So if you imagined that photons had mass, they behave like 1 over nu squared, right? You get a different dispersion measure for them. And that's exactly the 1 over nu squared that we saw. So you can get the best constraints on the mass of the photon can come from FRBs at the moment. The parameterized post-Newtonian parameter, you can also get best constraints from FRBs. And these are all relatively old papers, like they're several years old. If you were completely bored and didn't want to do anything innovative, you just wanted to do something mechanical, you could just get better constraints with the current data, right? It's all just sitting there. Techniques are sitting there. But it's worth waiting until there are lots and lots of repeaters at higher redshifts. Then you'll get phenomenal constraints. But these things are only interesting to a niche of the community who thinks that maybe photons have mass. Have you heard, put up your hand if you've heard of the Gershwin-Zeldovich effect? Yeah, oh, you've heard of it. I'm so impressed. Okay, so I hadn't heard of it. I love how everything I do, like, oh, it's all new, but it makes it all interesting. So this doesn't seem plausible, but if gravitational waves travel through a high magnetic environment, they can lose energy into the electromagnetic waves. So the two are coupled to each other and they can basically radiate as actual light. Yeah? All you need is large magnetic field in the way. So it's entirely possible that FRBs can either be constrained, this effect can be constrained, or that FRBs are coming from a gravitational wave that's passed through the environment of a neutron star or a magneton, and it's lost radiation into electromagnetic light. It's a lovely paper that Surajit and I wrote a couple of years ago. Almost nobody knows about this effect, right? But if you were to try to invent something, you can be guaranteed Zeldovich has already done it. So your question about the galaxy, if we've seen one in the galaxy. So the most compelling theories are magnetar-related theories. And that paper, it's not really a review, but there's lots of references within that paper. So if you wanted to dig around, that's the place to do it. But essentially, the most compelling models for FRB progenitors come from models related to neutron stars. They're not always all the same. And there's no single neutron star origin that can explain all observations. But the big embarrassment is that there's lots of magnetars in our galaxy, right? And we haven't seen any of these bursts. So in 2020, the first one was seen in the galaxy, which kind of bridges that gap and makes you feel a little bit less stressed that it's possible that there can be magnetars, but we still have to explain why the event rate is so low. And it may just be that you only get them from some evolution of magnetars. It may not come from all. This is just because not my original work. Tony and I just got to write the Nature News and Views about the observation. This was an observation. And it was a very important one because it kind of gives you hope that there would be bursts, that magnetars can be explanators. Also, it was an FRB coincident with X-ray and with gamma rays. So you see in multiple different parts of the spectrum, which is kind of incredible. And multiple different telescopes saw it. China slightly missed it, but Canada and I think Australia also saw it at the same time. So questions before I jump gears to talk about the future. Yes.
So do I understand maybe the one idea, it's kind of a plausible way. I think this gravitational wave shakes up the environment of a high magnetic field environment. This somehow gives you the EM reaction.
So if a gravitational wave travels through a strong magnetic field, then it radiates into photons.
Yeah.
Basically a term in the Lagrangian that couples the two. And so you can lose energy from your gravitational wave into photons. And that could be an FRB.
Okay.
Yeah. And the only way to test that is with LISA. The ground-based gravitational waves won't leak. Yeah.
So why not if it moves through charged particles?
What do you mean moves through charged particles?
So instead of using
magnetic field, you want
so instead of using just the accelerated charges instead of accelerated.
So the wave is moving through what is already a strong magnetic field. So there isn't really a current or a charge. I mean, I can't think of a charged environment that it could go through unless you built one. But yeah, okay, so the plasma is a different question and it's a good one. But I don't know that there is a Gertsen-Stein-Zeldovich effect for that, because I don't know if gravitational waves will change in that. I don't know if there is a, my guess, and I'm guessing this because I haven't thought about this, is my guess is that you're suppressed by 1 over c squared because of the relationship between E and B. You're asking about E and I'm giving you, and it's B. No.
You have to neutral objects and you have charge objects.
1 over c comes with the electrons, with the electric field. So if you're traveling through an electric field, the relative, I mean, maybe I should give you a calculation. But the coupling is suppressed by 1 over c squared, whereas with the magnetic field it isn't. So like if you look
so
at,
you mean the coupling between gravity and
yeah, so if you look at quantum vacuum experiments, do you know about quantum vacuum experiments? Okay, so there, the idea is that like the classic vacuum is just vacuum and the quantum vacuum is pair product, like making a, so if you wanted to probe nonlinear electrodynamics, you would pass a photon through and then your, they would interact with the imaginary particles before they've been reabsorbed into the vacuum. But you don't see it with a strong electric field, you only see it with a strong magnetic field. And that's, I think, because of the FF coupling, I think the 1 over c squared is in the wrong, is on the electric one. But I'm guessing that's the reason. I don't know for certain. I'm only guessing based on my knowledge of the lab experiments. In the lab, it's very easy to force the conversion with a kind of magnet that you would use for an MRI. But there's no way to do it with charge because you're off by order of magnitude.
You have much stronger magnetic fields.
That's right. That's right. And magnetize the magnetic field are much stronger. Yeah, but it's such a nice question. And my answer may be completely wrong. Okay, so to tell you about HIRAX, so this is a South Africa-driven experiment completely. And the history of it is that SKA, you all know, is coming and being built anyway. And at some point, the NRF went around to each university. I don't know if Roger was involved in any of this. They went to each university, huh? Oh, okay. So they went to each university and said, what would you like your flagship project to be? And KZN said, we want it to be HIRAX. I think UCT's is poverty or something. I don't know what Witz's flagship is. But each university has a project that's supposed to be their flagship. And then the NRF invests in that thing. And KZN were like, this is going to be our flagship. And it was like, you know, the astronomy community make decisions about experiments that are happening on a large scale. And they sit in a room, an annual town hall, and we discuss together. It's like just sneaked in, which is kind of amazing. And it's a relatively tiny experiment. He has a simulation of what the dishes would look like. But it should get a lot of the physics. Now I'm suddenly nervous I'm being recorded. It should get a lot of the physics that the SKA is aiming for, and it should get some of it earlier. So the frequency range is between 400 and 800 megahertz, which I'm going to show you why it's so great, but you already know that's in the radio because I showed you earlier. It's also the region where you would see intensity mapping of the baryon acoustic oscillations. It's the region of redshift where dark energy would switch on, right? Between 0.8 and 2.5. So in the continuous observing phase, you get your BAO, and in the like immediately seeing things, you get your FRBs. So there's two completely different science cases that are happening in parallel. And the BOA one is lots written here, but it's not really the point of today's talk. The point is that the transients are going to do amazing stuff for us. We have advantages over Chime simply because we are in the south. We have very low RFI because of this geographic advantage act I'm going to show you. And we have no snow. So our dishes are parabolic dishes. They have to have cylinders. And the crosstalk between cylinders is much worse than the parallel dishes. Oh, I should have highlighted that beautiful plot made by Shruti, my PhD student, just shows you the numbers of FRBs expected from different kinds of experiments. And you can see that HIRAX does actually very well. CORD is an American experiment that's also going to do very, very well. Okay, I don't know why there's nothing on there. Oh, right, Meerkat. So just to show you where HIRAX is, you all know the evolution of Meerkat. It's Karoo Array Telescope, yeah? And there were 7 of them originally, so it was called CAT7. Astronomers are very good at this. Meerkats live in the Karoo, and next to meerkats are hyraxes or rock dussies. I actually have photos of them from boulders. I should switch that photo. They're genetically related to elephants, bizarrely, because they're tiny and look nothing like them. And so hyrax is going to live next to meerkat, and hence hyrax. Yeah? You're with me? Okay. Particle physicists do not think this way when they come up into space. So you can see this is the band where we're observing, and the radio frequency interference is very low and very flat. And this is because of this geographic advantages. And there was, I think, a former astronomer sitting in Parliament in 2007 and got it passed in 2008. Compare that to some of the things that we get passed now. They're like, this was so visionary. Actually looked at the future of South Africa and said, this is a national asset. This is like gold or diamonds. And if we protect it, it will be an eternal asset for countries. So it's a really amazing thing that's been done. And I think it's given us a lot of leverage in international experiments. So these are the different prototypes. You can see we first hoped to have this one because we thought it would respond better to the wind. And the thing is blowing just as I said. Amazing. But it wasn't the case. In the end, we have to have the more solid dish that's lower to the ground. And the engineering is beautiful because they're 6-meter dishes, and there's a 3-meter height limit for how high you can drive on the national roads to get them to where they need to go. So apparently meerkat took their dishes at night so that they wouldn't get stopped. We're trying to get government permission instead. It's a different culture. Here's the first light. And this was a solar transit, and these are the interference patterns between the different dishes at Clairefontaine. It's not yet through, not yet on site. And this was December last year. So it's all very new and very exciting. And of course, I've put up the mirror trap image because these bursts are also coming in large numbers through meerkats, right? And there are all these multiple projects. And so we do have people in our group who work on mirror trap and on mirror lift. So mirror lift, in fact, Kira, if you remember in the beginning, mirror lift is the optical follow-up for mirror trap. And they use SALT, I believe, which is also an amazing national asset. So there's huge potential for discovery in South Africa with all of this stuff. And this was the first FRB discovery with mirror trap. And you can see lots of South Africans are on there. So a critical part for cosmology, the part that I really care about, is localizing the bursts. So if you have a single dish, you get maybe like an arc-minute resolution. So you can maybe say it's in this galaxy. But if you can get to sub-arc-second resolution, you can say where in the galaxy it is. So then you can isolate them to the edges of the dishes. And when we started talking, people said that'll never happen. And already now Chime are doing this. So we planned outriggers and we gave talks, and Chime built them immediately. So Chime has a huge advantage of actually being built, which is not the case for us. So you can see which part of the sky they will see, and we will fill in the complement. So you get information about the two. Oh, I realize I don't think I have a slide on this, but another beautiful paper Shruti did is looking at the patterns of where the FRBs have been observed, and if there's extra information we can get out of it using topological data analysis. So really nice techniques, math techniques to try to understand this. So the plan is to build these outriggers very far away. They're just sets of 8 dishes, and then it's as if you have a dish the size of the largest distance, right? So you get this incredible resolution. We also have to be very careful. I hate that bar is on top, but it says there is no typical FRB. So you always think that the first thing you see is typical, right? You see a white horse and you think, oh, this is a white. But that's not at all the case, especially not in astronomy. And I think that's a major warning for FRBs. The one that was very, very well observed, it repeats continuously, so it's extremely well observed, but it's totally atypical. And there is one burst that has been discovered with this VLA, the Very Large Array, and the host dispersion measure is 903. That is huge. So the host is contributing way more dispersion than the IGM. So when you plot them, they all sort of sit on a straight line. So DM to redshift is roughly linear, and this guy is just far out on the right on his own. So it's possible that there are total outliers. And if you were to use him for cosmology, your data would be wrecked because you'd accidentally have 900 flooding your errors. So I include this example just because one needs to be extremely careful in how you deal with this data. And then here's just like a a kind of summary of everything, I thought I have to give you one of these firsts. Somebody had a trombone, you could play the sad trombone for me. That's a sound. If I were to translate this into sound, it's a sad trombone. Wah, wah, wah. That's how all of them sound. That is every single one of them does this drift, has that drifting sound, but they don't all look like that. They have a totally different structure. Can't always tell where the peak is. Emma over here wrote somewhere up there, there you go, the bottom one, led this paper showing that the way that you estimate the dispersion measure, the localization, depends on your method. And so whether you can get it completely wrong where you decide your peak is. And so there's a lot to really be learned there. And on some level, we have no choice. It's going to be a machine learning problem. Or it's a blessing, depending how you look at it. But we're getting so many of them that we need to be able to figure out what's going on so that we can dump the data and move on. And there's a whole, way of doing this. And this is something that we're still going to have to develop with the HiREX pipeline now, but it's already being done. It's already being done for some of the other experiments. So we have a lot to learn from them, but also a lot to give back to the field. So in terms of wish list, which I put in my title, so I will give you one, is to see lots and lots of them. So technically there should be 10,000 in the sky every day. The 800 is that 800 number is in October, so by now there'll be over 1,000. Using them to cross-correlate with galaxy surveys should help us with cosmology in the long run. Getting more localized, so we don't have enough localization, so getting more would be amazing, and it would help us to, if we could understand the galaxies of origin. They seem to come from different types of galaxies, so there's no uniformity. High redshift bursts would be ideal for dark energy, possibly unrealistic, and multi-messenger counterparts. This was typed before the gravitational wave counterpart. We want to see neutrino counterparts. They've looked for them and haven't been seen, but as you can see, that doesn't mean they don't exist. But we would learn so much if we can get multi-wavelength and multi-messenger astronomy done with fast radio bursts. The rotation measure tells you a lot. So the high rotation measures mean that single magnetar evolution doesn't work. And you can learn about the intergalactic medium because you can learn about the magnetic fields in between. But we don't know enough to get anywhere. And we don't know enough to know whether they're different classes of these objects. So the advances are all completely intertwined. And my final slide, because I'm leaving nice time for questions, is the lessons for FRBs. So they were discovered with high time resolution data, so like rapid snapshots. And a lot of them were discovered in archival data. So they realized these can exist. Let's look back at our existing data. So the major revolution, conceptual revolution, came about without building anything. There was no tech advance that was needed to make the major understanding here. And I think that's a big one because we all sit around waiting for the next tech for the next thing. But actually, they did it with just looking at the same data in a different way. Now we're innovating with the tech because we know more what we want to find. But I think that's a takeaway message for whatever research field you're in, which is that looking at the same data in a different way may actually give you insights you hadn't thought of. The first one or few are not representative. You have to be very careful that you don't allow your own bias to creep into everything that you do, especially when there's limited resources. So we follow up the things that we've seen because we know where to look for them. You find people in their careers who write papers on the same thing over and over again because it's familiar and it's very, very risky. So you want to recognize that when you have limited resources, you are biased in what you follow up on, theoretically, scientifically, observation, everything. It's really important to look across the spectrum for what we might find. See, I'm worried about bias. If we cannot set aside our bias, we only find what we're searching for, not the things that we're not looking for. And from my side, as someone who's come at all of this in physics, you have to be extremely careful when using astrophysics as a laboratory because you're not in control of stuff and you have to really understand what you've read from papers, like our little FIGN thing where we thought astronomers have measured this. This is a number I can take as, but it's not, right? It's a number that it's their best guess. And so there's a huge potential for growth kind of going between these fields. So happy to take any questions.
So questions, yes.
What would you expect neutrino counterpart? And if the magnetron thing would have any series of other?
I don't expect it, but it doesn't. But I should look for them.
Yeah.
No, I don't know what to expect. I don't think they all can come from magnetars.
Sure. Are there any theories that have had?
I don't know that's necessarily, it's not necessarily that the neutrino is coming from the same source, but it's that you make it information by seeing the two coincident, right? And there is like ultra high energy observations.
Yes.
So that's kind of the idea, but it's the same with the gravitational waves. Like when we see them coincident with the gravitational wave, it may be from the same source, but it may actually just be information from the same place, not necessarily the same source. But I don't expect them.
So what would explain the coincidence? It's not the same source, it's just a coincidence. Yeah.
No, I mean, it could be from the same galaxy, but something is happening.
In multiple parts.
Yeah, or like
something sets off something else.
Yeah, I mean, why would, okay, so if you had two neutron stars merging, you would get a gravitational wave, right? And then you could also get a fast radioverse because there is the magnetar argument. The neutrinos is a different question. So for the gravitational waves, they're the same, right?
Sorry.
Go.
The chime astronomers telegram that we mentioned is very exciting. Have you got a sense of? I know it's just a telegram. Do you know what the nature of the gravitational wave is?
They just said either one black hole neutron star or two neutron stars, binary merger.
So it's a chirp signal.
I don't know. No. I mean, and
it's not something weird, it's basically.
No, I don't think it's anything weird. I think it was just a regular, and also they normally would trigger the VOE event. It's like a virtual observatory event trigger that tells everybody to look. I didn't mention this, but one of the beauties of Hyrax is it connects to Hess in Namibia. So they will switch on when they see, they will switch on and look. They can communicate with each other in time. So there are these triggers that tell everybody to look in that direction. And the trigger didn't happen. They had to take issue. And so nobody else got to look. So I suspect they saw it after the fact, right? So, but I don't think that there's anything interesting about the LRK, LIGO, yeah, LVK, LIGO, Virgo.
So they were all involved in the localization.
Yeah, yeah. And it's the same part of the sky, spatial, temporal, it's all the same. And it was a minute later. So that's the other thing is that they're not necessarily the same time, but now why is it a minute later? Because surely the gravitational wave is traveling slower, right? The gravitational wave is traveling at the same speed.
How fast was the star speed? It will just travel speed of light.
So should the photon, they should be the same speed.
No, photon goes to the median.
Oh, I see what you're saying. So it's not slowed down. So there you go. So there's your minute. It's the dispersion measure. Yeah, you're right. So there's your minute. So that's the delay. Yeah. But actually, you may be able to get a constraint if you get the exact dispersion measure. Sorry, I'm just thinking on the fly. You would get a constraint on the speed of the gravitational wave because you know the speed of the FRB. So if they're a minute apart, then in principle that could give you a new constraint. You know, the neutron star observations give you the constraints on the speed of the gravitational waves. They're not good. They're terrible.
Straight after it's like 1.7 milliseconds or something.
That's right.
Yeah, you're down radio frequencies, so you get the delay, but you can measure the delay because of the slope across the band of radio oscillations. So that's the extra constraint.
But that paper will exist. I'm guaranteeing within a few months that paper will come out getting a new speed of gravitational waves from them. Sorry, who wants to ask them?
This time, the actually see the position of the time.
I think they're now down. I think their resolution is better because they've got their outfigures going. But I don't know what the resolution is of that.
Then, the gravitational wave variant thing.
The localization of gravitational waves.
So then, the thing is,
are they? Is it enormous?
If it's got Virgo and Chiara,
3,
then it'd be way better. If it's just the US selection, so that's where it is. That's where it is. But I think
the same time within the same location, right?
What the time positioning.
The chime position is poor, but you know.
No, he's saying the gravitational wave position will be poor. Which position do you think will be worse? Chime.
depends on the Virgo diagram conclusion.
Yeah, I thought that would be
That should
good.
be better.
Chime.
Just chime. Chime's really good. It's very long.
You know, for the gravitational layer, like
If it's LIGO, it's a lot better if you.
But if you triangulate, right, then you get quite. I thought they get really good resolution. But just to be clear, when I tell you that an FRB is localized to a host, it is a very it's a best effort attempt, and I've asked these guys to explain to me over and over and over because my brain refuses to accept it. But they literally overlay the signal. I mean, there's one that the student presented to us a couple of weeks ago, and there's two hosts that are in the same image. They just decide which one, the closer one. So I mean, there's uncertainty in all of this. Maybe that's the best way to say it. There is uncertainty in all of it.
I guess that's factored into the 0.01%.
That's right. Yeah. But also, I guess patches of the sky. They work in how often you see them in patches of the sky, and the redshift must match, right? So they're matching, not just there; they're also matching the depth.
Any questions?
Sorry, one quick one. Do you care about how many classes of FRBs there are for the H0 estimation?
Yeah, I think so, because you get much better estimations with repeaters. So if I just do a repeater study, I get a better estimation than if I use all of them.
So you have to factor that.
Yeah, if you had, because it's as if you have, you have extra data, right? So it's more and more precise. And the more data you have, the better your H0 is getting. The H0 from FRBs fits where it would fit on that plot. It's not, there's zero surprises. But the more FRBs you get, the better it will be. I think that the H0 solution is a theory solution. I don't think the data is going to help us.
Yeah, systematics.
But how can they all have the same systematics?
Well, if you think of systematic as a different time in the universe, I guess.
Oh yeah. So I think that there's some evolution between the early universe and now, and that H0 has evolved. And that's the theory. No, there's all kinds of theories. You can have different, you could have a dark matter sector that is not coupled to the same G as us. That'll do it. But you have to test it in a different way. No one knows how.
Which side of the FRBs are they on the same side?
The short distance, so the same as the Cephals. They're not cosmological. They're not CMB. Yeah.
I watched some of FRB reply in frequency spreads. So what are those frequency spreading?
Then you mean? Well, I don't know if I know what you're asking, but I might have an image to show you. Just don't know how to find it. They look like bow ties, basically. Is that what you're asking? Have you seen the bow tie? That's how you know you have an FRB, if there's this bow tie image. And part of Shruti's project was, I didn't show her how to do this, to be clear. It's not my skill set. She learned from Ben Stappers how to turn those bow ties into the lala that I showed you. Yeah.
Is that at all clear? Is that sure?
It's clear to them, not to me. I think it's the sad trombone that you're seeing, and then there's a burst. So it's the drift, but it's frequency space. I'm not certain. I never actually touched the data. You have to be honest, right? That's why I have the math. Yeah.
Any last questions? If not, let's thank you again for joining us.